every night for the next decade. One telescope will film the entire southern sky, turning the universe into a living, breathing movie. When you picture an observatory, you might imagine a lone dome, aiming at a single galaxy for hours, teasing faint light from the dark. It's a beautiful practice, but it leaves vast celestial acres uncharted. Supernovae flare and fade, asteroids slip past Earth, and distant quasars flicker like cosmic Morse code, often unseen simply because no one was looking at the right patch of sky at the right moment. The Vera C. Rubin Observatory, perched on a Chilean mountaintop, was built to end that cosmic hide-and-seek. Its mission is radical in its simplicity: photograph the whole visible sky every 3 nights. Instead of a scrapbook of isolated portraits, Rubin will capture a time-lapse of the cosmos itself. Rubin's primary mirror is a marvel, an 8.4-meter piece of glass that cleverly combines 2 mirrors, M1 and M3, cast as one. That single pour saved weight, sharpened focus, and let engineers design a telescope barely half the length of others in its class. Sitting at the focus is the largest digital camera ever built for astronomy. Its heart holds 3.2 billion pixels. Imagine 800 HD TV screens stitched together. Each snapshot covers a patch of sky big enough to swallow 40 full moons. Point your phone at the same area, and you'd need to tap the shutter about 2.5 million times to match one Rubin exposure. Yet this giant doesn't dawdle. It will fire about 825 exposures every night, cycling through 6 color filters, from ultraviolet blue to near-infrared red, while a robotic carousel swaps heavy glass in seconds. The result? A rainbow record of the universe's every twitch and tremor. Each exposure, compressed losslessly, is larger than the entire digital archives of Hubble's first decade. Rubin will create around 20 terabytes of data nightly, filling a laptop's hard drive in under 10 minutes. Fiber links beam the torrent north to data centers in Chile and the United States, where supercomputers perform triage. Within 60 seconds of the shutter closing, the pipeline identifies anything that moved, brightened, dimmed, or newly appeared. A supernova in a distant spiral, an icy body beyond Neptune, an asteroid easing uncomfortably close to Earth. The system auto-generates an alert packet and blasts it onto the open internet, 50 million alerts every night, inviting professionals, amateurs, and artificial intelligences to take action. Behind the alerts, the raw images join a growing library. By the end of the survey, Rubin will have banked roughly 60 petabytes, enough to stream every film on Netflix for over 1,000 years without a repeat. Subtle cosmic microwave whispers tell us space is expanding faster each day, but the details remain fuzzy. Rubin will map billions of galaxies, measuring how their shapes are stretched by invisible foreground mass. Those weak lensing patterns act like topographic lines on a gravity map, letting scientists trace the distribution of dark matter and the influence of dark energy more precisely than ever before. Computer simulations predict swarms of faint dwarf galaxies orbiting the Milky Way too dim for current surveys. Rubin's deep-wide cadence is designed to spot these wallflowers, testing whether our leading theories of dark matter truly hold up on small scales. Every exposure will catch tiny dots crawling across the starfield, asteroids, comets, even elusive Planet 9 candidates. Estimates suggest the observatory could catalog tens of thousands of near-Earth objects and icy bodies beyond Pluto, sharpening impact, Trisk models, and rewriting solar system maps. Most thrilling are the surprises. When LIGO detects a gravitational wave chirp, Rubin can pivot and search the vast uncertainty patch for a fading kilonova glow. It may also uncover phenomena we haven't yet imagined, just as earlier all-sky surveys accidentally found quasars, pulsars, and gamma-ray bursts. Because Rubin's alert stream is public, a teenager in Nairobi or a retiree in Nevada can subscribe. Smartphone apps will flag a fresh supernova or the sudden brightening of a variable star. Citizen science portals built on the success of projects like Galaxy Zoo will ask volunteers to classify light curves, spot quirky lenses, or chase potential hazards. In this way, the observatory democratizes discovery as never before. The 8.4-meter mirror is now fully installed and gleaming beneath its Chilean dome. Rubin's 3.2 gigapixel camera, so vast that engineers literally sat inside the cryostat to wire its sensors, has completed final checks at SLAC, crossed continents, and is already seeing starlight. On the 13th of June 2025, the observatory released its very first engineering images. Razor-sharp star fields. These first light frames confirm the optics, camera, and data pipeline are all performing to spec. What happens next? Late 2025, early 2026. A short commissioning survey fine-tunes focus, filter swaps, and rapid alert software. Mid-2026. The decade-long legacy survey of space and time officially begins. Every 60 seconds, new exposures stream down the fiber link. Alerts for anything that moves or flares go public within a minute. Every approximately 2 years, Rubin will drop a full open data release. So classrooms, researchers, and backyard stargazers can mine fresh skies long before the survey is half done. The sky has already begun its close-up, and the movie camera is rolling. Rubin's archive will outlive us. Students not yet born will mine its database to study long-period comets, the motions of nearby stars, or the graceful spin-down of dying pulsars. The observatory pushes the frontier of cloud storage, machine learning classification, high-speed data networks technologies that sooner or later trickle into medicine, finance, and your living room devices. But beyond utility lies wonder. For the first time, humanity will watch the entire night sky in motion, not as a static backdrop, but as a living canvas. Every variable star will pulse before our eyes. Every galaxy will drift a hair's breadth across the detectors. Every unexpected flare will tell a fresh story. Rubin is not just a telescope. It is the universe's decade-long movie camera, capturing every flare, drift, and whisper in real time. And if a camera can unleash 60 petabytes of data, who or what will sift the cosmic haystack for needles? In our next crash course, AI astronomers, we'll meet the algorithms learning to hunt supernovae faster than any human eye. Stay curious.